Imagine if scientists can predict the behavior of materials before they are even created. That's the power of computational materials science. This scientific discipline combines the principles of physics, chemistry, and computer science to simulate the behavior of materials under various conditions. It's like having a crystal ball that allows us to peer into the molecular world and understand how atoms and molecules interact. Computational materials science allows us to design new materials with specific properties that can solve a host of real-world problems. From creating corrosion-resistant materials that can withstand the harshest of environments, to designing alloys with unprecedented strength, the possibilities are virtually limitless. Moreover, this field is accelerating the pace of material discovery. In the past, finding a new material was often a matter of trial and error, a process that could take years or even decades. Today, with the power of high-performance computing and sophisticated algorithms, we can simulate thousands of potential materials in a fraction of the time. But it's not just about speed. Computational materials science also offers a level of precision that's simply not possible with traditional methods. By simulating materials at the atomic level, we can predict their properties with incredible accuracy, reducing the need for costly and time-consuming experiments. In essence, computational materials science is a game changer. It's transforming the way we discover and design materials, making it possible to tackle some of the biggest challenges of our time, from climate change to energy storage and beyond. Now that we understand the importance of this field, let's move on to explore some of the exciting topics in computational materials science. Now that we've set the stage with the fundamentals of computational materials science, let's explore the role of machine learning in materials science, a rapidly evolving field that leverages data-driven approaches for material discovery and design. Machine learning, a subset of artificial intelligence, uses algorithms to find patterns in large datasets. It's like teaching a computer to recognize patterns and make predictions, much like a human brain, but with the capacity to process vast amounts of data at incredible speeds. In the realm of materials science, machine learning techniques are employed to accelerate the discovery and design of new materials. The process involves feeding a machine learning model with data about different materials and their properties. The model then learns from this data, identifying patterns and relationships that can be used to predict the properties of new untested materials. This approach dramatically speeds up the process of material discovery, taking it from a matter of years or even decades to mere days or weeks. To illustrate this, let's look at a few case studies. Researchers at MIT used machine learning to identify a new compound with the potential to be used in next-generation lithium-ion batteries. The model was trained on data from over 12,000 compounds, and it identified this promising material in just a few days. Similarly, a team from Northwestern University used machine learning to design a new polymer for use in solar cells. The model predicted the properties of the polymer with remarkable accuracy, significantly reducing the time and resources needed for experimentation. In essence, machine learning is becoming a powerful tool in the arsenal of material scientists, enabling faster and more efficient material discovery. It's a new frontier in material science, one that promises to revolutionize the field and pave the way for countless breakthroughs. Moving forward, let's explore the realm of computational fluid dynamics, often abbreviated as CFD. This is a branch of fluid mechanics that uses numerical analysis and algorithms to solve and analyze problems that involve fluid flows. It is a critical tool for understanding and predicting fluid flow behavior in materials. The principles of CFD are grounded in the Navier-Stokes equations, which describe the motion of fluid substances. These equations are powerful, but they can be incredibly complex and difficult to solve analytically, especially for turbulent flows. That's where CFD comes in. It provides a numerical approach to solving these equations, enabling us to make precise predictions about fluid flow. In the context of materials science, CFD plays a crucial role. It is used to simulate and analyze the flow of materials during manufacturing processes, to predict how materials will behave under different operating conditions, and to design materials with specific properties. For instance, in the production of polymer materials, CFD can be used to simulate the flow and mixing of the polymer melt, helping to optimize the process and improve the quality of the final product. To illustrate the power of CFD, let's look at a case study. Researchers at the University of Michigan used CFD to simulate the flow of coolant in a nuclear reactor. This enabled them to design materials that can withstand the extreme conditions inside the reactor, improving safety and efficiency. So, whether it's designing more efficient batteries, creating safer nuclear reactors, or developing new materials with unique properties, computational fluid dynamics is a vital tool in the materials scientist's toolbox. It's about understanding and predicting the fluid dynamics of materials and using that knowledge to drive innovation and progress. Computational fluid dynamics, a critical tool for understanding and predicting fluid flow behavior in materials, bringing us one step closer to the next big breakthrough. From the fluid dynamics of materials, we now transition into the world of high-performance computing in materials science. This is a realm where the power of advanced computing resources is harnessed to enable large-scale simulations and complex calculations in the study of materials. High-performance computing, often referred to as HPC, is a key enabler in this field. It allows scientists to model and simulate the behavior of materials at an atomic level and over long timescales, which would be virtually impossible with conventional computing resources. HPC provides the computational power needed to solve the complex mathematical models that describe materials' behavior, enabling scientists to make precise predictions and uncover new insights. For instance, in the realm of computational fluid dynamics, which we discussed earlier, HPC is used to solve the Navier-Stokes equations for complex, turbulent flows. In the study of quantum materials, HPC enables the simulation of quantum mechanical systems, which can involve calculations on an astronomical scale. To illustrate the transformative power of HPC, let's look at a case study. Researchers at the Oak Ridge National Laboratory used high-performance computing to simulate the behavior of a new class of materials known as high-entropy alloys. This work led to the discovery of new alloy properties, opening up exciting possibilities for the design of future materials. So, whether it's simulating the flow of polymers, predicting the properties of quantum materials, or discovering new alloys, high-performance computing is a vital tool in the materials scientist's toolbox. It powers the complex calculations and large-scale simulations that are driving breakthroughs in materials science, bringing us one step closer to the next big discovery. High-performance computing, powering the complex calculations and large-scale simulations in materials science. First up, quantum materials, a field that explores topological insulators, superconductors, and quantum computing materials. Now, to understand these materials, we need to step into the world of quantum physics, where the rules of the game are a little different. Computational exploration comes into play here, providing an invaluable tool to probe into these fascinating materials. We use computer simulations to predict and understand the behavior of quantum materials. For instance, topological insulators, unique materials that are insulators on the inside but conductors on the surface. These properties have potential applications in quantum computing, and simulations help us glean insights into their behavior. Then we have superconductors, materials that conduct electricity with zero resistance. Understanding these through computational means could revolutionize power transmission and magnetic resonance imaging, among other things. Finally, there's the realm of quantum computing materials. These are the building blocks of quantum computers, which promise exponential speedups over their classical counterparts. Quantum materials, an exciting field with endless possibilities made accessible through computational exploration. Next, we discuss thermoelectric materials, where simulations aid in the design and optimization of materials for waste heat recovery. In the realm of computational materials science, simulations are more than just a tool, they're a guiding light. Specifically, when we're talking about thermoelectric materials, these simulations are crucial for design and optimization. Let's consider what thermoelectric materials do. They take waste heat and transform it into useful energy. In a world where energy efficiency is not just advantageous but necessary, this process of waste heat recovery is vital. But creating these materials is no simple task. This is where simulations come into play. By providing a computational model of thermoelectric materials, scientists can manipulate and optimize their properties before they even exist in the physical world. They can predict how these materials will behave and make adjustments accordingly, leading to more efficient and effective designs. Thermoelectric materials, turning waste into wealth with the help of computational design and optimization. Now we turn our attention to uncertainty quantification in materials simulation, a crucial aspect of assessing and improving the reliability of computational predictions. It's all about gauging the accuracy and precision of our simulations. In the realm of materials science, it's not enough to simply make predictions. We need to understand the degree of certainty behind them. Uncertainty quantification allows us to measure this, often using statistical methods. It's like a safety net, providing a buffer against potential inaccuracies or errors. It can help identify areas of potential improvement or adjustment in our computational models. In the grand scheme of computational materials science, this is an invaluable tool. It's the compass guiding scientists to make more accurate, reliable predictions. Without it, we could be steering blind, leading to wasted resources and misdirected research efforts. Uncertainty quantification, ensuring the reliability of our computational predictions, a critical aspect of computational materials science. As we come to the end of our journey through computational materials science, we hope you have gained a deeper understanding of this fascinating field. We've taken a tour through the vast landscape of computational exploration, from quantum materials and thermoelectric materials to the realm of uncertainty quantification in material simulation. We've seen how computational methods are transforming the way we explore topological insulators, superconductors, and materials for quantum computing. We've also discovered the role simulations play in designing and optimizing materials for waste heat recovery. The importance of these computational strategies extends far beyond these topics. They are the backbone of creating advanced alloys, piezoelectric materials, and materials designed for extreme conditions. They help us understand environmental degradation processes to design more durable, corrosion-resistant materials. We've also discussed the power of high-performance computing in materials science and the advances in algorithms and computing architectures that are driving this field forward. From soft matter and polymeric systems to the design of catalysts for chemical synthesis, the applications of computational materials science are as diverse as they are impactful. Moreover, we've touched upon the role of AI and machine learning in microstructure optimization. These technologies are helping us predict and design materials microstructures for specific properties, opening up new possibilities in material science. And let's not forget the exciting world of wearable electronics and sensors, where computational design is revolutionizing the way we create flexible and stretchable electronics. In a world where sustainability is a key concern, computational strategies for environmentally friendly materials are more important than ever. They play a vital part in our quest for sustainable and green materials. So, you see the importance of computational materials? Science in the design and discovery of new materials cannot be overstated. It's a field that's pushing the boundaries of what's possible, transforming our understanding of materials, and paving the way for the innovations of tomorrow. Thank you for joining us on this journey through computational materials science. Stay curious, keep learning, and see you next time.